So let us begin with the ninth problem in this series. The ninth problem in this series is problem number 1.207, and the problem is stating a planet of mass small m moves along an ellipse around the sun so that its minimum and maximum distances from the sun are equal to r1 and r2 respectively. Find the angular momentum of this planet relative to the center of the sun. So as we approach this problem, let us explain the situation diagrammatically. So this is the situation which the problem is discussing about, where r1 and r2 are the minimum and maximum distances, and we have also marked the velocities at the two instants v1 and v2 respectively. Capital M is the mass of the sun and small m is the mass of the planet. Now the question is asking us to write the angular momentum expression for this planet relative to the center of the sun. So if we think in terms of the length of the semi-major axis, so over here we can say that the length of the semi-major axis is equal to r1 plus r2 by 2. So therefore if we say that the total energy associated with this particle, so we can say the total energy associated with this particle, total energy, so this can be written as minus g small m capital M upon A. So twice of A, the distance between them is 2A. So if we write it this way, so where A is the length of the semi-major axis, so over here if we substitute this value, so we get minus g small m capital M upon r1 plus r2. So this is the first important thing that we need. So the next that we say is that as the planet moves in elliptical path around the sun, the angular momentum is conserved. So we can apply angular momentum conservation, that angular momentum at position 1 is equal to angular momentum at position 2. So therefore m v1 r1 is equal to m v2 r2. So this we are referring as equation number 1. The next one is if we write energy at any point, so let us take point 2. So if we say total energy expression at point 2, so the total energy expression at point 2 will consist of a potential energy term, a kinetic energy term, the sum of which is equal to total energy. So over here we can say that the value of potential energy is equal to minus g small m with capital M and small m upon r2 plus kinetic energy, that is half m v2 square, and this is equal to total energy. So using the expression in terms of the semi-major axis, so we write it as minus g small m capital M by r1 plus r2. So this will serve as equation 2 over here. Now from here we can solve for V2. So if we solve for V2 in terms of R1 and R2, then we get V2 equals 2g ms R1, or we can just write capital M, which is mass of the sun. So 2gm R1 upon R2 R1 plus R2. So we get an equation like this for V2. Now hence if we write the angular momentum at point 2, hence angular momentum at point 2 can be written as m v2 r2. So over here if we put the value m v2 r2, so we end up getting m 2gm r1 r2 upon r1 plus r2. So we get an expression like this, and this is the final answer for this problem, that is problem number 1.207.